Okay, I'm going to start right now. It's 10 o'clock. About 5 students today attend some sort of the workshop, so they are not coming. So I expect about 7 people coming in today's lecture. About 5 장대준 교수님's workshop. They have a workshop, so that's fine. So whenever you have to attend not only workshop, conference, just to let me know, then you can just do. Okay, Wednesday I start this underwater explosion. Again for 6 weeks, I will accelerate to cover as much as I can, but some of you like Yonghyun and Kyungsuk and Gaulgi, I'll give you the additional the files that you can read. So that's what I expect. But this is really a first section rather than saying a first chapter. It's a process or procedure, you can say. Excitation, as we did Wednesday, excitation, then response, in the process to compute the response. There is approach. First, in the approach is modeling the complex system, and the second is prediction, is a simulation, simply speaking. First, excitation. Excitations in our cases, as we know, explosions. So excitation can be grouped into 2, conventional explosion, or some people call the chemical explosion, but it's the same. So one is conventional explosion. The other one is a nuclear explosion. Nuclear explosion, we are not going to touch nuclear explosion. That's another big area. But since Russia collapsed, we really don't talk about the nuclear explosion. But lots of informations for conventional explosion you can share with the nuclear explosions. So for the conventional explosion means TNTs, HBX1, HBX2, 3, 4, RDX, C4, all kind of the chemical compositions, the explosive has it. So here for conventional explosion, I already talked conventional a few times, just to remind you, that's the concentration we're going to do. And you can think of air blast, underwater explosions, internal explosions, and contact explosions. Our concentration is underwater explosions. Air explosion, different name is AIREX, AIREX, air explosion. That's another art, but we cover a little bit in the gas explosion. But gas explosion is very much different from conventional explosions. So air blast or air explosion consists of shock or fragment. This fragmentation is giving the damage. Some of you know the bomb which explode when the airplane dropped the bomb. It exploded in the air. then right in the air is scattered, the fragment just scattered all over. Then as it comes down, it could again explode. So there are lots of modern weapons. This is the area we're going to really concentrate. The explosion below the water or right at the interface between air and the water. So underwater explosion, shock wave it generate, reflection wave it generate, or refraction wave it generate. Refraction wave is same as a transmitting wave. So we'll discuss a lot more as I give a lecture. Then bubble, this bubble means a gas bubble, so we'll talk, this is just the introduction. So, and the cavitation. And internal explosion is another heavy area. In gas explosion, we discussed about an hour in the last lecture. Here, internal explosion, some of you, most of you involved in explosive, the Birkenhead problem, naval problem. That's what the internal explosion is. So whether you like it or not, you will really involve in internal explosion. But here in the class, I'm going to teach underwater explosion, which is right here. But you, as I introduced overall what's involved here, then you can tell where the underwater explosion fits. So that's kind of important. Nuclear explosion, again, air explosion, underwater explosion, surface explosion, they divide into the three area. But again, we are not going to cover on this, okay? So explosion, excitation, and the response, what I'm dealing for the defense problem, this all underwater explosion problem is really defense problem set. It's not the ocean structure, offshore structure, but some terrorist act, they really throw the bombs, things like that, then it can, then you have to, even if it's offshore structure, you have to handle the explosion device. I gave a lecture in the Construction Technique Institute in the Ilsan about a month ago. They invited me because they want to know the explosion in the water. I said, why do you need explosion in the water? You are dealing with a civil engineering type of the structure in the water. They are planning to design a tunnel in the bottom of the sea, connecting between Korea and Japan, someplace in Korea, someplace in Japan. And they worry about the submarine could travel quite below the water, and some explosion problem is one of the accident problem they identify, so they have to explore underwater explosion effect on the tunnel. So, wow, what are you doing? But that's the situation they are considering as one of the excitation item, which is explosion. So now you are in the position to compute the response. So what kind of the response do you want to compute? So in the defense area or underwater explosion area, you are dealing with two target objects. One is a surface ship response. It's just for the naval ship type. Or commercial ship is the same thing. Then in the surface ship response, equipment is what you have to worry about. All kind of the equipment for surface ship. Everything is, all the equipment nowadays has computer chips, computer systems and all that, which is very prone to shock or acceleration. So acceleration, high acceleration usually kills the chip because it's very brittle material. So you have to worry about the survivor of the equipment and the hull structures and the deck house structures and so on. That's what you want to really know, the safety of the, mostly you can generally say equipment. For submarine response is concerned, of course you have to deal with the equipment and you have to really deal with the stiffened hull structure and pressure hull penetration. What does it mean, penetration? Pressure. Submarine hull is a pressure hull, but you have to worry about the hull penetration. What's the hull penetration, Yongyun? What does it mean, hull penetration? Very important. In the surface ship, not important like a submarine. Submarine has torpedo hatch. So torpedo hatch, before you release the torpedo, the hatch has to be opened, then closed. And lots of equipment is really attached on the hull. And water has to be pumped out and pump in through the hole, right on the hull. So it's a chunk of equipment attached on the hull in the submarine. For the explosion situation, chunk of mass attached on the hull, very, very sensitive or detrimental to the explosion. Why? Kyung-suk, why? I will wait until you guys don't talk, then I will wait. See, Abdullah, can you think of something? Why? That's called the hull penetrator. Hull penetrator, the chunk of mass attached on the submarine hull. Some valve, sea valve, is heavy mass attached on the hull. Valve, water's in and out. So when you have a shock on the hull, then chunk of mass times acceleration, what do we have? Inertial force. Heavy inertial force effect is very detrimental to the survivor of the hull. In surface ship, it's not a problem because that's usually above the water. Any hole on the hull which release the waters and so on is not a problem because above the water. But submarine penetration, very important for design. You are going to design for some simple design you're gonna do. So that nature, because submarine you never assume it's floating on the free surface. If submarine is if you worry about the submarine floating on the free surface, that's wrong design. When the submarine leave the harbor, they always dive. As they leave the harbor, it just dive and go down to the operating depth, whatever that is, and will not come back up the free surface. So until they come back to the harbor, always has to be sit under the operating depth. So in that sense, if you watch the movie, something like Red October, and there's a few submarine movies, and the 571. Nobody asked me for video movie, so I think you looks like all saw before, so it's good. Some submariner, they really worry about the explosion. When they shoot the torpedo, then they identify automatically their location. Once enemy ship knows the location, then that's a problem. Then they have to really dive and stand still down there, and they have to turn off all the machinery, because otherwise they radiate the noise enemy can detect right away. So, they start to drop the bomb. So survival is a problem. Anyway, so submarine response and surface response is what we are considering as a response. For ocean structures, some portion is really below the water, like all the piping systems and all that. If there is a shock, then they have to use a similar approach to calculate the response of a neighbor ship and submarine. And the modeling. So modeling and simulation. Modeling. Empirical, there are two techniques usually. One is empirical analytical technique, or you can simply say experimental modeling. And within this, then you can think of scaling and modeling and statistical samples and testing procedure and the equipment you have to worry about it, and things like that. Here is conventional underwater explosions and nuclear. We don't really worry about this nuclear. So here, nowadays in U.S. Navy, they are using the DDAM methodology, which is called the Dynamic Design Analysis Method, which is something like about 50 years old methodology. They started in Second World War, then, not started, DDAM starts in 1960 to really find a way to conduct analysis and design using the Second World War, the experience. So the DDAM is really solving the dynamic problem using the static analysis approach, which is covered in Chapter 8. chapter 9. But again, as a part of this course, for some of you, except Abdullah, it's good to know. If you have a chance, I kind of suggest go through chapter 8, chapter 7, 8 and 9, which is not difficult at all. And that's what we are using it, still using it after 50 years. They start by Naval Research Lab, NRL, in early 60s, now still using it. So it's so amazing, over a 50 years span. And I think the Korean Navy is also using it. And the shipbuilder, Hyundai, Daewoo, Samsung, you name it, they're using it. In U.S. Navy contractor, they have to use it. Otherwise, Navy is not going to approve. But this validity of the approach, strictly speaking, not very good. But it works. So that's why they keep using it. It's interesting. And testing procedures and experiment, submarine hull stiffened model and the closure model, all kind of the experiment is what the U.S. Navy's conducting. And that's lacking in Korea. They are doing the experiment and test, but compared to U.S., almost none here. Everything is done in simulation, and they feel that's good enough, but trend is keep changing right now. And surface is showing right here. Submarine testing in U.S. Only done once by putting the whole submarine in the near the surface, the telescope you call it, right, is above the water, and this is in operating speed. Then they put the charge and bang onto it. It's Yorktown. Once they have done. But all small tests, component test is concerned, hundreds of different times they have done. But the reason was, why just done once? Admiral, I think he was a 3-star, not 4-star. The Admiral Rickover, we call him as a nuclear Navy Admiral. He started nuclear submarine business. Then before he retired and passed away, nobody dare insisting to conduct submarine testing. Nobody can touch the submarine except him, so not allowed. But once they did, after I think he retired. I think it's Yorktown. So beauty is to conduct the experiment using the actual ship. That's what the strong point in U.S. Navy. And England, they have done some. And Australia, they have done some. So here, for the submarine, there is a so-called SSTV model. SSTV model is a segment of actual nuclear submarine. They built exactly same as nuclear submarine section, midsection. Then It's not the full section. It's I can tell the length of the SSTV. SSTV, as I shown here, that means it's a submerged shock testing vehicle, or some people call as a submarine shock testing vehicle, usually SSTV. We don't have it here. We don't need a nuclear subsection, but we need something like a Korean existing submarine, which is a diesel-operated submarine, or we need 장보고 submarine, which is still not built yet in the design stage, but they could build. 영현, 서대위님, when you become admiral, you should insist we should have SSTV. Then we can conduct the testing using actual submarine section. About for 20 years, whenever I met the admiral, I said we need testing in Navy, and we need SSTV and FSP. FSP is another platform for the surface ship. SSTV is for submarine. So this SSTV, how much it would cost? Less than, in Korea, less than maybe $300,000. Not bad, $300,000. How many ok? 300,000, 3억, 3억. Not bad. And that's for the submarine test vehicle. And then so for surface ship is a floating shock platform. It's like a large barge. Abdullah, you know what a barge is? It's a floating, floating platform. It's a barge. If you go harbor, they have a barge. It's a flatbed floating on the surface of the water. FSP is called. Then they install lots of different surface ship equipments and they conduct the testing. How many do we have in Navy? None. This is about the same cost, about 3억. It's about $300,000, not much. But of course, you need all the sensors, data acquisition systems and all that. So eventually you need something like $500,000, which is about 5억. Some rich people can donate 5억 easy. One couple donate the 400억 to build the building. Anyway, so that's what the modeling, the experimental technique. Just to put that in mind, the modeling is not just for the mathematical modeling. Experimental modeling, that experimental testing is what we need. So that's what we need, then we can really build a database and we can use it for survivability analysis. But of course, some people can say, well, we can just borrow from other country. They don't release such a data because it connects directly to the naval ship or the important vessels. They don't release that. Then their data is good to study for their ship survivability. If we use other country test data, it's good for their ship, not good for our ship. So what we have to do is we have to conduct using our ship configuration. Then we can build the database, then we can really conduct the analysis for survivability study. Otherwise, I don't see what's good for it. Another approach in the modeling is mathematical modeling. So mathematical modeling, you can divide this into the air and water. So you can study in air's penetrations, you can study, then for the water, it's an air-blasted situation. Water is structure-medium interaction. This is really FSI, fluid-structure interaction. Everybody looks like teaching FSI, but FSI in their field, in their concentration, is what fluid-structure interaction means. Like Professor Park is really expert in the acoustic structure interaction, and Higyo is working on acoustic structure interaction. Why acoustic? Acoustic means really shock wave and structure interaction. The beginning of structure medium interaction. Medium could be fluid. And for gas explosion area, medium could be the oil or oil oxidizer mixture. And beginning is Taylor flat plate theory, which is really basis, simple, very nice basis on what is FSI. That's what I'm going to introduce. And another one is a DAA, doubly asymptotic approximation technique. And Tom Gears developed this not from some theoretical source, but by empirical sense. He put the equation together and building the first order, second order, the approximation. And nonlinear Sandler approximation, Golden, the Costanzo. Golden retires years ago. Costanzo is still working for bulk cavitation computation. And overall surface ship response, this is very simplified, beautiful approximation technique. But he retired some years, at least 20 years ago he retired. Renat, he retired, I think last year. So I'm going to show you some, okay? Then you can feel it. And the computer code predictions for surface ship, as we are using it, LS Dyna itself for near field explosion, and for far field explosion, we are using LS Dyna combined with the USA or Nastran USA. So either software predicts really well, okay? But we are going to use this USA and LS Dyna. So right now I think Gaulgi and Dr. Kim, you have to really go through, not this. In 1995, when I was in Naval Postgraduate School, we first used Nastran combined with the USA. At that time, only the implicit integration technique was available. So you can handle the large size of the FEM model. But for that time, LS Dyna has explicit and explicit integration scheme only. So this is much faster. So we switch from here to here. Since then, we use this all the time. But nowadays, Nastran has explicit integration schemes implemented a few years ago. And LS Dyna, they didn't have implicit integration scheme. But now they have. We needed that to conduct a modal analysis to get the modal shapes and natural frequencies of all that. So nobody tried it because this is really for the transient response computation purposes mostly. But this is what we are using it. And some people say, why don't you just write the code for this? Whoever say that, he doesn't know what the LS Dyna doing, how complex this is. John Hallquist developed LS Dyna since 1970. So it's about 40 years, day and night. He's still writing the program, Fortran program, which is very similar to, not identical. So this is, I gave you this as an overview and to let you know what's going on around. What's going on around in explosion. What kind of explosion you will encounter. But here is for defense purposes. But Abdullah, you're not in the lab. You're in the lab of Professor Akimoto, so which is really not the fuel mixture. So you're not. So in that sense, it's okay. But as explosion, learning explosion, this is one part, very heavy part of explosion. Another part is really the gas explosion. It has common things quite a bit, so in that sense it's good. Okay, any questions? This is just an overview, just drawing a big picture before getting into the smaller part. Then from now on, from chapter 2, like 2.1 through 2.4, I'm insisting you must know 100%. But again, 2.1 is within the underwater explosion. I'm going to explain what is underwater explosion, what does it do. That's a part in 2.1 I'm going to cover. So we get narrowing it down. Again, air rafts, air explosion, underwater explosions, learning the phenomena is very important. Okay, then after that, mathematical expressions will go through. In chapter 2, underwater explosion phenomena 1, and next is the 2. This is from the book written by Robert Coles. Some of you has that book, Robert Coles. So, Robert Coles. The title is Underwater Explosion. If you insist on me, I really like to have that book, I can provide you. I have a couple of extra books, but Abdullah, you don't need a book. But learning here is good enough. Maybe Dr. Kim, I gave you one? No? It's called The Underwater Explosion, written by Professor Cole in 1946. It's an old book. but that's the beginning. You have one? I don't think Hyung-sung needed, but Higyo has one kind. So this is really covering the phenomena. I feel the way I explained would be good enough to understand the context phenomena. I taught this kind of classes many times for the last 25 years. Going, traveling throughout the world, it was fun. Everything was free. Accommodation, room and board, all free. So a sequence of underwater explosion event, order of what's happening, physical laws and properties. So first initial condition, starting from what's the explosion? What is the explosion? I'm talking about the explosion of TNT, RGX, C4. That's sort of the explosion, chemical explosion. So material means it's really explosive, and explosion occurs. The TNT material is, I said, very unstable material. Then when I say unstable, it's always you have to concern about the, what does it mean stable, unstable? Some relativity that you have to be concerned. Is it unstable means if I touch it, it's going to explode? But TNT is not the explosive which is sensitive. No. You can, of course, if you just have TNT and drop it, by the impact it could explode. But if you just handle with the care, that's good enough. Okay? It's like a powder. TNT is really powder, and they put it together. Last April, we went down to Kimhae area. We conducted explosion testing. Dr. Kim was there, Yong-han, Higyu. Hyung-suk was there too, right? When we do the explosion test. You were there, right? So that's not exactly TNT, similar to TNT, but for mine explosion situation, they use that immersive dynamics, dynamites. I forgot the exact name, but I handled it. Everybody handled it. They just mold it to make a spherical size, shape, which is okay. But if it happened in U.S., you will never ever touch the explosive. At least 50 meters away, you have to put the small tent and store the explosive. Very safety concern. But here, I don't see they kick around the dynamite, the ball. But that's what we can do. In other words, TNT is not greatly sensitive for the impact. Of course, if you drop, it could be okay, it could explode. So shouldn't, but you should carry with, you should handle with the care. So unstable compound. Explosion, what is the explosion? I define the explosion of chemical explosion as explosion such as TNT is a chemical, this is a good definition, chemical reaction in a substance which convert the original material into a gas at very high temperature and pressure. Very high temperature and pressure it released as a result of explosion. Then it becomes very stable gas. That's what the human nature is. That's what the natural things wants to do. Everything from unstable into the stable environment. Exactly the same thing. So what's explosion? Chemical reaction in a substance which converts the original material into a gas at very high temperature and pressure. This explosion happens in the water. In the water, heat is absorbed through the water rapidly. So when you're dealing with underwater explosion, you don't have to worry about the heat problem. So heat parameter is out for underwater explosions. Okay. If it's air explosion, then what happens? Heat is a concern. For nuclear explosion, heat is the main concern. Radiation of the heat is main concern. And when you simulate the nuclear explosion, what the U.S. Defense Department did is whatever I talk is unclassified. What they have done is in the desert area. Nevada is a desert in U.S. and Las Vegas. Just away from Las Vegas is all desert. So in the desert they built a tower, huge tower. I forgot the height of the tower. And they put the small buildings. Just I don't know, I forgot what's the radius, where side length of the radius to build around the structure. What they did first to simulate the nuclear explosion is a thermal shield in front of the structure. Because in the nuclear explosion situation, heat is coming. Heat just kills, melt the structure before the shock wave really hit. Very, very detrimental. So even if it's high strength steel, when the heat hit the first, it's going to melt and all the material properties change. Then what's good to analyze it with the material, using original material property done. So what they did at the top of the tower, they put something like 40,000 pound or 100,000 pound explosive at the top, very high. Then around here, they put the structure. Then they put the thermal shield. Before they explode this, they ignite the thermal shield to give a similar explosion in the amazing. So that's what you have to concern. High temperature and high pressure. For underwater explosion problem, then you have to worry about the shock pressure and interaction with the submerged target, okay, whatever that is. So that's what you have to concern. Submerged target, pressure, temperature, not a factor. And the explosion is concerned once it happens, you can't stop it. Gas or oil problem, same thing. Gas plus oxidized or the mixture of oxidizer with the fuel. Once explosion occurs, you have to keep away and let it finish by itself. But for chemical explosion, the time it takes is not long. The physical explosion, the time it takes is a millisecond, order of a few milliseconds, 1,000ths of seconds. So everything is done so quickly. But you don't have to provide oxygen to really burn. It just happens by itself. Gaseous reactive component. Usually TNT is gray or white material, but after it explodes in the water, if you see it, it's all black stuff as a remaining powder. High temperature, 3,000 degrees in Celsius scale, is different from the gas explosion in a sense. Pressure, 50,000 bar, amazing. But gas explosion, we are talking about the few bars, or less than 1 bars dynamic pressure, but as you look at 50,000 atmospheric pressure, which is about 7.35 times 10 to the 5th power psi. Pound per square inches is US, but I'm insisting no both, not just the metric, not just the US gravitational, but nowadays you have a hand phone, then you can touch, and you can nowadays one hand does everything, and all the conversion you can do. So 1,000 psi is how many megapascal? I looked at the other day, it's about 6.9 megapascal. So that you can convert. Unstable to stable condition. Self-sustaining after the initiation. Once it explodes, it will go whether you like it or not. It propagates very fast. At the beginning, when it explodes, so it's going to generate the detonation process associated with the detonation velocity, which is about 8,000-9,000 per second. Then it converges into the acoustic speed in the water, which is about what? About 1,500 meters per second. You already heard a few times before about this possible. Okay, I'm going to stop right here, and as all other students coming in Monday, I will accelerate them. But you have my notes and everything. And some of you saw that as I hand out sometime before my short course note, 3-hour lecture in the conference almost every year. But some of you has that, but that's not the whole note. The important features that cover there. So anyway, you have my notes and read before you come into the class. Okay, half the class is not here today, but at least my students are here. Okay, I'll see you Monday.